O dabar girdėsime dar vieną pranešėją. IT saugumo specialistas Vytautas Butrimas saugumo ir informacinių technologijų srityje dirba jau bemaž 30 metų. Jis yra dirbęs anksčiau Krašto apsaugos ministerijoje, šiuo metu jis rengia NATO Vidurio Europos kibernetinės rizikos tyrimą, o savo pranešime jis aptars kritinių infrastruktūrų kibernetinį saugumą. So please welcome Vytautas Butrimas and brief introduction to the Cybersecurity Dimensions of Critical Infrastructure. Please welcome.
Good morning, everybody. I'm going to give you my most sought-after presentation. I've given this 4 years in a row in a lot of venues. The NATO school at Oberammergau has asked me to do this 4 times. They're asking me again, and each time they give me more time. I started out at a half an hour, then an hour and a half, and an hour and 45 minutes now. I'm going to try to compress that into 30 so we have time for the coffee break. So I'm not going to waste time, I'm going to get right going. The cybersecurity dimension of critical energy infrastructure. A brief introduction. Why is the word energy in brackets? Because you can substitute any other critical infrastructure. What I say will apply not just for energy, but to water supply, transportation, even medical infrastructure. And I think you'll see that as the presentation continues. Just a few words about the center that I've been delegated to work now for 3 years from the Ministry of Defense. The NATO Energy Security Center of Excellence. We're here in Vilnius on the grounds of the Military Academy. What are we here to do? We assist NATO, nations, and partners by supporting NATO's capability development process, mission effectiveness. We provide expertise on energy security. Here we are doing a week-long lecture and energy tabletop exercise in Kiev. Here I am in France looking at a pipeline system looking for cyber risks. This is one of our experimental devices, solar power, wind power, to help troops work in the field that have a base with some portable energy supply. And for more information, just look at the website or come in over and visit us. A little bit about myself. Somebody said I have almost 30 years of experience. Well, I started out as an IT guy, working in North America as a technical support guy. Then I started working in the defense and security policy area. And I work in exercises, crisis management, table talk, national. I'm a member of some industry work groups, the INISA, Industry 4.0, Industrial Internet of Things work group, the International Society for Automation, the 62443, the Industrial Automation and Control System Security group. I'm a co-moderator of the SCADASEC list. This is where you can sign up. Many of the things that I'll be talking about today have been discussed in this group. Even this morning, we're writing letters to each other. Mostly engineering people, operational technology people here, and some IT. I also put on my cyber Don Quixote hat to try to save the world from cyber. I'm also a member of the Research Advisory Group for the Global Commission on the Stability of Cyberspace. I've contributed to a lot of reports, articles, and guides. Here's a handbook on SCADA control systems. This is a chapter from me, something for INISA, Ukrainian cyber study, articles that I've published, and from the OSCE and so forth. So you can find me on the internet and read, or I'll send you some information if you are interested. There are important differences to consider. The previous speaker mentioned industrial control systems. Okay, this is the point of my, where I'm going to be talking about today. We are very comfortable talking about IT things. This is the IT comfort zone. Most of the people that work in government with IT policy, they're coming from this background. They're worried about denial of service attacks, web defacements, email viruses attached, and so forth. This is talking about information. What I'm talking about, what I've been studying for the last 10 years, is the operational technology, where there is a process going on. You have the word SCADA. How many of you have heard of SCADA? Okay, this is a big term. HMI, Human Machine Interface. This is the little Windows computer that you use to find out information about what's going on here. The Industrial Control Systems Network. How do you know what an RTU is? A PLC, a DCS. How do you know what a relay is? By the end of my presentation, you'll know why they are significant. This is a program logic controller. And I'll continue on with this. You'll know what that is and why it's so important, and unfortunately, it is now a target. They've been targeting this area for a long time. IT people are pretty familiar with what to do. But the people that work here are sort of, you know, who's trying to attack us? Why are they doing that? What do we need to do? This is the area that needs attention. Information technology space. This is a picture of one of my offices at the Ministry of Defense. What is this security focus? Confidentiality, integrity, and availability. Confidentiality is that password, you know, it's like this long, it's hard to remember what it is, so you have access to a system. IT is used to being the center of attention. If it goes down, the whole office goes down. You go out for a cup of coffee, wait for the administrators to reboot the server or whatever. But nobody dies when the IT goes down. That's the kind of point I'm sort of overemphasizing. In industrial control system space, you're remotely monitoring and controlling a physical process. You know, nuclear reactor, hydroelectric dam, electrical distribution for a national grid, high voltages, kilovolts, and so forth. What you're trying to achieve is not the confidentiality. You want to make sure it is safe. Safe for the people that are working on the power grid, and safe for the customers that are getting the electricity, that their circuits, their TVs don't blow up on them. Confidentiality is at the end. As a matter of fact, passwords, I mentioned IT is big on passwords. Here they look at it differently. They don't want to have to look what the password is at 3 o'clock in the morning if they have an emergency. So that's why you might see a password 1234 and 12 operators use the same one. You have to get into the system to do something. So you're trying to secure a desired process state. You're not trying to save a document, data, information. You're trying to make sure the electricity goes normally, the fuel down the pipeline goes normally. You don't want to have a physical result. This is a 1,500-ton hydro electric dam, rose 50 feet into the air, killed 75 people. It's a failure in the safety system. What is a safety system? Okay, they're monitoring and controlling a physical process. We call it operational technology, control systems. A little bit deeper into that, they use basic process control systems for normal operations. Okay, what is that? Think of your human body. Okay, when you had breakfast this morning, you had the coffee, you had the orange juice, you had the toast, the eggs. You ate that. But you don't tell your body, okay, push this egg down to this, add this chemical there. It's all basically, it's a basic process control system. You don't need to intervene and tell it what to do. Your body knows what to do, normal. Then you have a safety instrumented system. These are programmed emergency actions to protect the facility and its people. Again, safety is a priority. What's it trying to do? Before the human can respond, something happens serious with a millisecond. You got to do something. It brings a critical process back to a safe state to avoid loss of life and damage. Okay, think of the human body again. You get a virus, you get bacteria, you get sick. Your safety system of your body raises the temperature. You get a fever, antibodies are produced. It's trying to bring your body to a normal state of health. Again, you don't think about it, it's an automatic reaction. Here's the Deepwater Horizon. You might have heard about this a few years back. Gulf of Mexico, millions of gallons of crude oil spilled into the Gulf for months from an oil platform in the Gulf. There were 8 safety systems in place. I talked to a BP executive about this. This is where I heard about this. Only one of them needed to work. Unfortunately, all failed, and this is what happened. the end result when the safety system fails. I'm going to come back to this importance of safety systems later. But this is why we're talking, people can get killed, property can get damaged in operational technology control system sphere, which is a little bit outside of IT comfort zone. Okay, what is an operator of a power grid, power plant, water supply, water treatment? What are they worried about the most? They're worried about losing the view and the control of a critical physical process. This is the Fukushima reactor station after the earthquake and tsunami. It has no power in the control room. They don't know what's going on in the reactor. The physical process is going on, but the IT is down, but the physical process is still going on. The reactor is going into meltdown, and the safety systems, the pumps, the coolant is not working because they don't have electricity. You don't need to use an earthquake or a cyber to do this. You can do this, or a tsunami, you can use a cyber as well. How about this? What is this? This is the result of someone doing data development work on a computer in the control system network. How many of you have done data development work and have this happen to you? That's what happens when 25,000 gallons of gasoline flow into a river, and the operator thinks everything is normal, it's all green, but he didn't realize the data, the telemetry that told him about the link has frozen for a minute. And he's making mistakes, he's seeing a drop in pressure, he's adding more in making this worse. Somebody was fishing by the river through the cigarette, 3 people killed, and the water plant that was getting water from this river was destroyed as well. This is what we're talking about, the situational awareness. You're trying to remotely monitor and control a critical process. The communications is a very key issue. And you don't have time for delays. 1 minute delay on what's going on in a critical process can end in a disastrous result. What's been going on? Okay, IT is coming to the industrial control system world. Okay, it used to be analog, manually controlled. Now it's becoming digitalized. Lots of functions and devices, and it's remotely controlled. This is how things looked like 50 years ago. It's one engineer, he's next to the device that's working on the physical process. Now it's one guy sitting at a big board and he's watching how the national power grid is working. This IT is helping to do that. You don't need as many people. You don't need to send people down the electric line every day to check. You put a device on and it tells you everything is okay. But you really depend upon your technology. And unfortunately, that is starting to become a focus for malicious actors. If you don't get this IT and ICS, you're going to make mistakes, especially if you're making policies. This is a true story. The government set out a draft regulation for cybersecurity to the operators of critical infrastructure. And they got a letter back, and it was a very strange letter. It says, the draft cybersecurity requirements state that they are intended to address critical information infrastructure, in brackets, including industrial control systems. Now, this is the interesting reply. However, your draft requirements do not address industrial control systems. It's a response from a utility operator. You can think of the government guy, I'm doing a great job, I'm going to help the country with these cybersecurity regulations. And then give it to the utility operator and they get a response like this. There's a disconnect. It's a sign that people aren't talking to each other. It's a sign that the engineers are not part of the process of policy making. IT security measure is not adequate to protect an industrial control system, and we're looking at a physical process. This is a true story, a nuclear reactor safety system. There was a IT guy got a job working for this reactor power station, and he saw, oh look, there's a computer that doesn't have the Windows update, that doesn't have the patch, so I'm going to patch it. It's a very good IT security practice, but you don't have the knowledge of what it's connected to. Okay, this is a cooling system for a power station. While that computer was frozen in its update mode, the safety system stopped getting data about the state of the coolant in the reactor, and it scrammed the station. That's an emergency shutdown of the reactor because there's no data coming to the safety system about the state of the coolant. You don't want to have a Fukushima incident. This is why when you visit an industrial site, for an IT guy, it's like a shock. We don't patch because it's considered an unacceptable industrial risk. If you understand something about what they're trying to do, they're trying to be safe, and they're trying to make a system available to the public, you understand why they're a little worried about applying a patch. They want to avoid having something like this. How many of you have heard of the word iceberg? Most of you. There's a new word coming out, and there's a website you can look up. There's 4 different meanings for it. It's called cyberg. Okay? The real threat is the part you cannot see. You know, a lot of these cyber incidents and things like Stuxnet, you might have heard about, they were announced publicly, but they were in the field for years. They're below what you can see in the water. You know, it turns out it was possible to reach across sessions and violate security boundaries for nearly 20 years, and nobody noticed. This was like from Google's Project Team Zero. They found a vulnerability 20 years old. It's a couple weeks old news. And even if you try to explain what is the concern, what are the issues, you'll find that there's like this captain of the Titanic mentality. You know, sir, we have reports of icebergs in the area. Some ships have stopped for the night. This is April 12th, 1912. Captain says, let's keep going. We're going to make a speed record. A cyber-related condition whereby a threat or warning of a possible threat results in either the misinterpretation or misunderstanding of a given situation, resulting in a decision with no corrective action. That's the definition that I contributed. You can go to the website, you can see what the German BIS also contributed. But this is the problem of the raising the awareness, and what do you do when you have it? I'll give you some ideas of what you can do towards the end of my presentation. This is something very interesting, came out about a month ago. How many of you have heard of Vxworks? Raise your hand, Vxworks. Okay, after 29 years, I only heard about this last month when the first report came out called Urgent 11 Vulnerability. It's a vulnerability in real-time operating systems. Real-time operating systems. Okay, we're thinking about Windows, Linux. There's a delay, you can wait. Real time means you got to do it immediately. Electric power grids are very important that things are synchronized. You can't have things late by a few milliseconds. It has to be real time control and reaction to events. Compromised controller, in an industrial controller here, for example, could shut down a factory and pawn a patient monitor. It could have a life-threatening effect. And it's like in 25%, this one particular operating system, Vxworks, is about 25% of the world's programmed logic controllers, remote terminal units and drives closest to the industrial process. You know, I'm talking about Schneider Electric. They came out with about 12 patches and advisories about this particular vulnerability. Okay, here's a safety system by Schneider. Can be hacked now. Nobody knew about it. There was a cyberg. It's been around, and now all of a sudden, what are you going to do about it? The technology can be used against us. The laws of physics can be used against us. This is a picture of I don't know how many ton diesel turbo electric power generation, lots of kilowatts. The Idaho National Laboratories in the United States wanted to do an experiment. Can you mess up a power generator like this using cyber? So they set up a notebook computer 12 kilometers away. They simulated a power plant and a power grid. And yeah, they got in. they started playing with the phases, turning it on, turning it off, turning it on, just giving simple commands, got around the safety systems, and the torque involved in stopping and starting something that's several tons spinning, it turned this into a brick. They call it the Aurora Vulnerability. It's a vulnerability that you can't do anything about. It's part of laws of physics. It's in every rotating electronic device that we have. And if you connect something to an Aurora, a device is having this event like your TV or your computer, that'll also be gone as well because of the unbalanced electrical that comes out of that. Okay, what threat emanating from cyberspace is the most worrying? And for those who are trying to defend critical infrastructure, I mean, we've got hackers, we've got cybercrime, it's script kiddies, we've got all these. Well, what's the one that really is the one that should be of concern, but maybe doesn't get the attention it deserves? It's the malicious activities of states. These like, the 007, they have the license to do something. If they need some technical support, they have the queue to come up with all the gadgets and the ways to break into something. And they won't quit until they achieve the objective. Like James Bond, he reaches his target, otherwise the movie is over. This is what a state advanced persistent threat is like. And Stuxnet was the first one in 2010 that was publicly announced. If you read Kim Zetter's book, Stuxnet was around since like 2003. It just came out of the cyborg realm. Cyber weapon used by a state against a critical infrastructure of another. The target had no apparent connection to the internet, air gap. They got in. It did what? Caused a loss of view and loss of control. Okay, these operators didn't know what hit them. These centrifuges were having problems. They disabled the safety system that should have responded to the attack to bring the spinning rates down to a safe speed. They were disabled. Again, it's a bad idea when you forget about your safety systems. It was a high-tech operation, cheap for a state, deniable. We didn't do it. Most people know which countries, and as a matter of fact, Kim Zetter came out with an article this past week, added another country to the list of those who worked on the Stuxnet operation. There's still a lot of information worth studying in here. So what happened after Stuxnet? Well, it's sort of the idea caught on. And it just didn't happen in the Middle East. It happened in Europe. This is the BSI State of IT Security in Germany in 2014. They issued a public report. You can still get it on the internet in English or in German. It was a targeted attack on a steel mill. They found a foothold in the office IT. And that's usually, by the way, where the attack stops. Your usual low-skilled cyber attacker, he can get into the office IT, but you need special knowledge to go into the control systems because of the safety devices in place. They went a step beyond. They learned about the OT, and they caused a loss of view, sounds familiar, and loss of control of a steel mill smelter. They couldn't shut it down, and it just ended up causing physical damage. Evolution. Ukraine was mentioned. Okay, I won't go too deep into it, but again, just a few weeks ago, security company Dragos came up with a further study of the second cyber attack in Ukraine against the power grid. Not the one in before Christmas in 2015, but the one that took place a year later in December of 2016 to Kiev. The city of Kiev was partially blacked out for a few hours. And they looked into this study. There's something suspicious here. They went further into the code. Okay, a lot of people were saying, well, Ukraine responded very well. They went to manual control. They re-energized, they re-established the power grid. They went back to manual control. And so they were really surprised to see in the 2016 attack, there were attempts to go after the relays. Now, the electrical relays are safety systems in the electric grid. This is why you have cascading blackouts. It could be like a small cause, but it ends up, the whole region, the whole country goes down. That's because the relays are tripping and they're isolating systems and devices. They're isolating things like 110 kilovolt transformers, because if it stays connected to the grid, the load is being sent around. You can destroy that. So by going after the relays, it really made it risky to go to manual control. Because if you can't trust your relays, you might start to re-energize your systems, make your connections, and you have no safety. You can cause this real damage. So the power doesn't come back after 3 hours. It comes back maybe after 6 months until you get the generator that's 15, 20 tons to be manufactured, or the 120, 300 kilovolt transformer is manufactured and transported to the site. You don't keep these spares in the garage all over the place. They're expensive items. So this is, it's getting spooky. In Ukraine, I was in Ukraine in 2017. I mentioned that course in tabletop. I spoke with the power grid operators there. Ukraine is like an experimental laboratory for cyber attacks. A lot of people think, Ukrainians, they use the old Soviet. No, they use ABB, Schneider, Emerson, Honeywell. So they're updating all the systems. So whoever is attacking them is getting a lot of practice on attacking the systems that are used in this country and in Europe and in North and South America. There aren't too many manufacturers of this equipment. So that's a spooky thing for the future. Triton Hatman. Okay, advanced persistent threat. Caused 2 plant shutdowns in the Middle East. One of the biggest oil refineries in the world. You can watch on YouTube. There's a lecture from a guy who was a first responder. And what's interesting was the plant suddenly shut down in June of 2017. It was a Schneider Electric Triton triple redundant safety system. Why did it shut down? Why did it cause this? So they sent the controllers to the manufacturer, to Schneider. Schneider did an engineering diagnostic analysis, and they said everything checks out fine. This was just some sort of anomaly, something. And they put it back online to the plant. Everything was running normally again until August of that same year. 2 months later, much more major shutdown of the plant. Then they brought in a cyber investigation unit on that, and they discovered that, hey guys, someone's been in your plant control systems for over a year. And you know what they've been doing? They've been planting programs, and they've been reprogramming your safety systems. That's a real escalation. Whoever's attacking, they don't care if they kill people or destroy damage. You blow up an oil refinery, that's hydrogen sulfide gas, toxic. It'll take years, months with special clothes to go in and clean up the mess. This is what they're trying to do. They didn't have the full knowledge to execute the attack. This attack, the safety system smelled the rat, and they shut down the plant. They weren't fully disabled yet, but they were trying to do it. So that's what's interesting about this event.
Vytautas, the plant shutdowns are definitely an interesting thing to do, and to talk about, but let's continue and move to the coffee break.
Okay, I'll just conclude with my last slide.
That's something to catch up.
Okay, in closing, I apologize for going over time. Remember the lesson of the 3 little pigs? Only one got it right. In terms of recognizing the threat, it's not just cybercrime. It could be other more skilled actors that you need to make a house of brick. Beware of applying an IT security solution to an ICS environment. Don't let an IT guy come in there and tell you what to do. If you're an operator, have the engineer give the final okay. International cooperation is the key. And again, when you develop a policy to protect critical infrastructure, invite the engineers, not as an advisor by the wall, but he's an equal partner who can provide the necessary imagination and also feedback on what will work and what will not work and what are the concerns. And that's it. Thank you very much.